Now this is lecture 10, and since I have covered a portion of this chapter, now it's time to solve some numerical problems based on half cell, complete cell and Nernst equation. So this is part 1 of lecture 10, and I will cover 8 to 10 numerical problems in 3 to 4 parts. Now this is the first problem. It is given that calculate the redox potential of the half cells 1. This is one half cell. Here you see a platinum rod is dipped in a acid solution and hydrogen gas is bubbled, maintaining the pressure 1.5 atm. The solution is very dilute. And 2, you have another half cell. This is an independent problem. Here you are also getting a platinum rod which is also dipped in a HCl solution, dilute, and chlorine gas instead of hydrogen is being bubbled at a pressure of 5 atm. Now you have to find the redox potentials of these two half cells. Now we will start with the half cell 1. So for half cell 1, here it is given to calculate the redox potential. So it is not mentioned whether you should determine the oxidation or reduction potential. You can do anything, no problem. But in convention, it is preferred, it is desirable to express the potential, if not mentioned, in reduction form. So let us express the redox potential in reduction potential format. So to have the reduction potential, first let us write the half cell reaction in the reduction form. So this is the half cell reaction in the reduction form. Here you have 2H plus 2 electron, arrow H2. So solution from the H plus from the solution will take up electrons and will convert to hydrogen. This is the reduction part, and if there is oxidation, in net there will be conversion of H2 to H plus. So in that case H2 will leave the electron share and will come to the solution in the form of H plus. Now we have the reaction to occur in both directions. One is the electrolytic solution tension when H2 pass into the solution in the form of H plus, and another is osmotic pressure where H plus takes up the electron and comes to gaseous form. And it depends in which direction. It depends on the counterpart or the another half cell with which it is connected, which reaction will occur. If this half cell is connected to another half cell which is more electropositive than this one, having a higher oxidation potential, then it will act as the cathode, and if that electrode with which it is connected has a lower oxidation potential, then it will act as anode. So it depends on which half cell it is being connected. The charge of this electrode depends on which half cell is connected to this half cell. But in this problem we will not get any other half cell, and we don't have to combine it to form a complete cell. We have to concentrate only in this half cell. So let us consider this reduction reaction to be occurring at the given electrode, that is 2H plus 2 electron, arrow H2. Now if you are able to write the reaction, and here actually equilibrium is attained, there is electrolytic solution tension and there is osmotic pressure, and the forward reaction backward reaction occurs, and at a time come when equilibrium is reached within this half cell, so that we have a electrical double layer that is responsible for the development of the charge on the electrode. So it is a reversible reaction, and for reversible reaction we will be able to write the Nernst equation. We know the format. Sorry, this is not cell, this is half cell, and since we are writing in the reduction format, let us write here 2H plus arrow H2. Here it will be E0 2H plus. This vertical line is indicating that there is phase difference between this solution and this phase. So this is aqueous liquid phase and this is gaseous. So this vertical line is indicating the phase difference. Now E 2H plus H2, that is EMF of this half cell, is equal to the EMF in standard state minus temperature. Is it given? No, temperature is not given. So you have to write here 2.303 RT upon NF. Now see, 2 electron transfer is occurring here. So you put, or rather I will put it in the next line, NF log, here it will be pH2 by concentration of H plus whole square. Is it okay? Nernst equation looks like this. Now this is the standard hydrogen, this is the EMF of the standard hydrogen electrode, and in convention the standard hydrogen electrode is supposed to have zero EMF. It is considered, and I will discuss about standard hydrogen electrode and how to find the standard EMF of any half cell in next lecture, that is in lecture 11, but in not the other parts of lecture 10. In lecture 11 I will discuss regarding that topic. So we will put here 0 volt, it is the convention, and if it is given 25 degree centigrade, then we will be able to write it as 0.0591. So let us consider that temperature 25 degree centigrade is given. So you put here 0.0591 by N. You see here is, this is a 2 electron transfer reaction, so we will have 2 here, and we have log pH2 by H plus whole square. You have to write here 25 degree centigrade. You must mention it. Now one thing I have discussed in lecture 9, that if someone write this equation in the form H plus plus electron arrow half H2, what will happen? If someone writes the reduction reaction in this format, what will happen? Will it be able to change the EMF? If you can remember, you see, I have told you that it is not going to change the EMF of the half cell or cell. Since if you write in this format, your Nernst equation will look like EH plus half H2 equals to, it will be 0, and you have minus 0.0591 by 1 here, since there is a single electron transfer, and here it will be log, see, it is pH2 to the power half by H plus, by H plus, third bracket. Now see, if we multiply here 2 and divide here by 2, what we will get? We will get 2 here, and 1 2 will be, there will be another 2 in the numerator. I am taking it to the within the parenthesis of logarithm, so it will enter in the form of square, so it will give you pH2 to the power half square, so it will be pH2 and it will be H plus concentration and square. See, these two look similar. Here also you have minus 0.0591 by 2 log pH2 by third bracket H plus whole square. Here also you have 0.0591 by 2 log pH2 by H plus whole square. So your way of writing must not control the EMF of half cell or cell, and that must be. EMF of cell will depend on the nature of the electrode, nature of the solution will depend on temperature, but it will not depend on you about how you represent the reaction. So whether you write it in H++ electron arrow half H2 or 2H++ 2 electron arrow H2, it will not carry any difference. Now, is this value given? You check the diagram. Here it is given that pressure of hydrogen is 1.5 atm and the concentration is this one. So, if we represent this cell representation of half cell, not cell, it is half cell, it will look like here platinum, or rather, since I am depicting in reduction potential, we must represent it in H+, 2H+, arrow H2, sorry, not arrow, it is a vertical line representing the phase difference, and here it is platinum. So it will be aqueous, it will be gaseous, and it is solid, and the concentration here is C equal to 0.01 molar, and the pressure is P equals to 1.5 atm. So this is the representation of this half cell. Now we put the values. Pressure is 1.5 and H plus whole square, it is 0.01 whole square. This is 1.5 atm, we put it in the numerator, and in denominator we write 0.01 whole square. Now we need calculator. So it will be 1.5 divided by 0.01 square, and we have to take logarithm of it. So log answer, and then into 0.0591 equals to divided by 2. So it is, or E 2H plus H2 equals to minus 0.1234 volt. So at 25 degrees centigrade it is 0.1234, right? So at 25 degrees centigrade you are getting the EMF of this half cell to be minus 0.1234 volt. So if you represent it in oxidation potential, what will be the value? We know E oxidation equals to minus E reduction. Just by changing the pattern, it is going to change the sign only, but the magnitude will remain the same. So it is reduction. See, 2H plus is getting converted to H2. So this is reduction, and if we represent it in the form of oxidation, that is H2 is getting converted to 2H plus after releasing electron, then it will be of the same value, just the sign will be opposite. So it will be plus 0.1234 volt. So this value we have obtained. Now we have to check whether we are correct or not. Now see, if the standard electrode potential is 0 volt, then what should be the voltage when the pressure of hydrogen is kept at 1.5 atm and the concentration of the solution is kept at 0.01 molar. So let us judge the thing. when you keep it as 1.0 molar and you keep it as 1.0 atm, that is, you keep pressure of hydrogen to be 1 atm and you keep concentration of H plus to be 1 molar, then it is giving you the standard state and it is 0.0 volt. Now the condition given here is it is 0.01 molar. So concentration is decreasing here from 1.0 molar and pressure is 1.5 atm. So pressure is increasing from the previous one. Now if we write it in the form of equilibrium, what it actually is, then you see with increasing pressure there will be a greater tendency of hydrogen molecules, dihydrogen molecules, to come into the solution. So this is going to increase the electrolytic solution tension. With increasing pressure, with increasing pressure from 1 atm to 1.5 atm, tendency of oxidation will increase and we will have a boost in the oxidation part. So it will increase compared to the osmotic pressure. Now see, you are decreasing the concentration. Now if you decrease the concentration, then the osmotic pressure will decrease accordingly, and if the osmotic pressure decreases, then the tendency of liberation of H plus in the form of hydrogen after taking up electrons will decrease. So this osmotic pressure will decrease. So the condition taken here is favoring the oxidation process at this electrode. You are increasing the pressure, so the tendency of H2 to get into the solution increases, that is oxidation, and you are decreasing the concentration of H plus ions, so the tendency to get liberated after taking up electron decreases, that is reduction decreases. So oxidation tendency increases, reduction tendency decreases. So there must be an increment in the oxidation potential from this value, and see, you got here EH2 to H plus equals to plus 0.1234 volt. So the oxidation potential is increasing from this value to 0.1234 volt. So this is the answer. Now we will come to solution for the second problem. Now in second problem, you see Cl2 is pumped into this HCl solution, maintaining the pressure 5 atm. Now here it is given that half Cl2 bar Cl minus. So we must write it in this format. Though actually there is no difference, since it is given in this format, I request you to not to get into the contradiction. So we are writing in a reduction format, that is half Cl2 plus electron arrow Cl minus. But you see, actually reaction occurs in both directions, so that we get equilibrium after a certain time from the start, and when the equilibrium is attained, we will get an electrical double layer that is going to decide the charge of this electrode. Now the Nernst equation, which will be like this one, half Cl2 Cl minus, it will be connected to E0 half Cl2 Cl minus, this is in standard state, minus 0.0591. I have considered 25 degrees centigrade in the previous problem, so it will be maintained, and there is one electron transfer. So here it will be log and Cl minus concentration by P Cl2. See, this is the Nernst equation. Now, what is this value? This value is supplied. So you put here plus 1.36 volt minus 0.0591 log, you put the value of Cl minus, it is given 0.15 molar. HCl is a strong acid, so it will dissociate 100%. So you get the Cl minus concentration to be 0.15 molar. And PCl2 will be 5 atm. So again you need calculator. So it is giving you plus 1.45 volt. Within the logarithm you are getting a fraction which is less than 1, so it will be negative, and this negative will be negative will be positive, so it will add up, and we are getting a enhanced reduction potential. We are getting an enhanced reduction potential. Now if this is the reduction potential of the cell, then what will be the oxidation potential? This is Cl minus. It will be of same magnitude but with a different sign. So you see, this is the reduction potential and it is positive. So it will show a tendency to get reduced, and this must be since Cl2 is electronegative and it has a tendency to catch electron rather than releasing it. So tendency of reduction is greater, so it will have a positive reduction potential. So its oxidation potential will be negative obviously. Now we have to judge a thing that whether at the given condition this result will be obtained or not. This is a checkpoint. So you need not to write it in exam, but just for your satisfaction that I am doing it correctly, you have to check this. Now when you take this pressure to be 1.0 atm and take this concentration to be 1.0 molar, what it will give you? It will give you the reduction potential in the standard state, and it will be plus 1.36 volt as given, supplied in the problem. Now what you are doing? You are switching from 1.0 atm to 5.0 atm. So you are increasing the pressure. So if you increase the pressure, what it will happen? You are adding more reactants. So the equilibrium will shift to the right and will be re-established as per the last Chatelier's principle. Since you are increasing the pressure, the reactant concentration is increasing, so it will move forward to give more and more products. So the equilibrium will be shifted to the right and will be re-established. So tendency of getting reduced will increase. If the forward reaction occurs more, then tendency of forward reaction will increase. Now we are taking this concentration to be 0.15 molar, that is, compared to the previous case, compared to the standard state, we are taking it as it in very small concentration. So the osmotic pressure of this ion will decrease, so it will show a greater tendency, it will show a lesser tendency to go into this side. So the backward reaction will be less since the osmotic pressure decreases. And if you consider the last Chatelier principle, you see the product is getting lowered, so the equilibrium will shift in that direction in which the product is obtained. So forward reaction will increase. So both the conditions, that is decrease in the concentration of the electrolyte and increase in the concentration of this gas, chlorine gas, is favoring the reduction process. So what will happen to the reduction potential? The reduction potential must increase from this value. And see, we have obtained this enhanced value, which is E0, sorry, it is E. We are getting the enhanced value 1.45 volt from 1.36 volt. So our solution is correct. Now we'll deal with the next problem. I will deal with the next problem. Next problem given is problem 2. EMF of an electrode Mn plus changes by, you write it in your copy, 0.02 volt for 10-fold increase in concentration of Mn plus, then find the value of N. This is the next problem. So another half cell is given. It is an unknown metal dipped in a solution containing its own ions. Valence is not known. And it is said that the EMF of this half cell, that is single electrode, changes by 0.02 volt for 10-fold increase in the concentration of the ions. So find the value of N. So let us write the half cell reaction. Let us write it in oxidation format. You have freedom to write in any form, but I am advising you that you please prefer the reduction part. But if you write it in oxidation mode, examiner will not cancel it unless it is mentioned. But it is desirable since reduction potential, representation in reduction potential is the convention. So you are writing the half cell reaction in oxidation potential. So it is M. So there will be equilibrium. Not equilibrium, I rather say there is a reversible reaction. I am mentioning it equilibrium, but equilibrium will come after a certain time when I am just dipping the metal within the solution containing its own ions. The reaction is starting. Both the electrolytic solution tension, that is from M to Mn plus, and the osmotic pressure, that is Mn plus to M. And after a certain time, the rate forward will be equal to the rate backward, then only equilibrium is said to be achieved. Now what the problem is saying, that you are increasing this concentration by 10 times. So what will happen? If you increase the concentration by 10 times, then the osmotic pressure will increase. So this is electrolytic solution tension, this is osmotic pressure. So this will increase if you increase the concentration by 10-fold. And if it decreases, it will come to this electrode after taking up electrons. So it will favor the reduction part. Increase in concentration will favor the reduction part. So reduction potential will increase and oxidation potential will decrease. Hence they are telling you that the EMF changes. They are not saying you that it is decreasing or increasing. Since if you represent it in oxidation potential. You see, with increase in concentration, the backward reaction increases, so the oxidation tendency decreases. So there will be decrease in the oxidation potential by 0.02 volt. But if you express it in reduction potential, then with increase in concentration of the ions, the osmotic pressure will increase, that will prefer the reduction, and what you will have? You will have more tendency to get reduced instead of getting oxidized. So the reduction potential will increase by 0.02 volt for 10-fold increase in concentration. That's why they are saying that it changes. It is not telling that it is increasing or decreasing. So you have to write the Nernst equation. So the Nernst equation for this half cell reaction is, you mention it here, the Nernst equation for the given half cell reaction is, these are the formalities, you have to maintain it in exam. So it is E m mn plus equals to E0 m mn plus minus 0.0591 by, so there are n number of electron getting transferred, so it will be n here, and it is log mn plus by am, it will be 1. Now see what will you have to write here. Please say, I can't hear you, but you have to say that whenever I write this, I must mention here temperature. If I put here 0.0591, then I must write here 25 degrees centigrade. This is mandatory. And since am equals to 1, this equation will be like log m n plus. Now there are two cases. Say m n plus 1, for which the E cell is one, and when the concentration taken is Mn plus 2, the EMF will be Mn plus. See here it is telling that for 10-fold increase in the concentration. So I am taking two different concentrations, Mn plus 1, Mn plus 2. And for this concentration we are getting the potential to be E1, and for the second concentration we are getting the potential to be EMF to be E2. So you will get two equations that will look like E1. I am not presenting the half cell notations any further to reduce my labor. So it is E1 equals to E0 1 minus 0.0591 by n log, and that is Mn plus 1. And for the second case it will be E2 equals to E0, 2 minus 0.0591 by n log Mn plus, this is 1, this is 2. Now see, I have given tagging of 1 and 2 here. Is it correct? May I have the power to tag this standard state by 1 or 2? See, where from this 1 and 2 tagging coming? This tagging is coming due to difference in the concentration. For this concentration it is 1, for this concentration it is 2. But for standard state the concentration of the ions must be 1.0 molar. So this tagging is unacceptable. If you take this, then the examiner will understand that you don't know the science behind it. So we got two equations, 1 and 2. Now equation 1 minus equation 2, that will give you E1 minus E2. So this will cancel out, and see, this will be minus, and this and this will be minus of minus, so it will be plus. So let us take this in front, 0.0591 by n log mn plus 2 minus 0.0591 by n log mn plus 1. Is it okay? I am subtracting equation 2 from equation 1. So this will be E1 minus E2, and this will be E0 will cancel out, and minus this. Now minus of minus, that will be plus, so it will come in front. So this is 2 minus 1. Very easy problem. So E1 minus E2 equals to, you take it as common, n log this concentration by, so it is mn plus concentration plus 2 by mn plus 1. Negative outside logarithm, so it will be in parenthesis, they will get divided. So this is the equation. Now you see, if the concentration increases by 10-fold, then this will be the relation, mn plus 2 equals to 10 times mn plus 1. Now if this is increased, then the osmotic pressure will increase and the oxidation potential will decrease. Now we have expressed E in the form of Mn plus, that is in the form of oxidation potential. So oxidation potential will decrease. So E1 greater than E2. With increase in concentration, the oxidation potential decreases. Since E1 is greater, we will have here 0.02 volt in place of this difference, since it is saying that the EMF changes by 0.02 volt. So the EMF changes by E2, and you have the difference E1 minus E2. This one is greater, since the oxidation potential will decrease, E2 will be less, and the change given is 0.02. So this will be 0.02, 0.0591 by n. It will be log. Here we put the relation, so it will be 10 into mn plus 1 by mn plus 1. It will cancel. Now log 10 equals to 1. So you get n equals to 0.0591 by 0.02. See, this log 10 equals to 1. You take n to the left hand side, and we take 0.02 to the right hand side. So it will give you 2.955. It will give you 2.955. Now this indicates the electron transfer. So number of electrons cannot be fraction. So it implies n equals to 3. So it is given that find the value of n. So it is a trivalent metal. M is getting converted to M3 plus, releasing 3 electrons. This is the answer. So we will perform another 2 or 3 problems in part 2. Practice these 2 problems, and I'll also practice other problems from your textbook, and stay with me for part 2 lecture.